If you remember from general chemistry, when we talked about chemical bonding, one of the types of bonds we had were covalent bonds. And so in a covalent bond, what you have is a pair of electrons. Typically, each bonded atom is going to contribute one electron, and those two electrons between the two atoms are going to be shared. So if we see the example here on the screen, each hydrogen atom is bringing its one valence electron to the relationship, and if they overlap, then they will be able to form that covalent bond, that sigma bond. Now, when we look at the amount of energy and the different types of forces that are in play, we've got obviously attractive forces, but there's also going to be repulsive forces. When those particles get close enough to one another, the nuclei are going to push off of each other, as well as the electrons. As much as the electrons are involved in the bond, electrons are all negatively charged, so there's going to be some electron-electron repulsion as well. And so to find that sweet spot where you have the balance between the attractive forces and the repulsion forces, that's what gives one of these bond energy diagrams the shape that it has. And so, again, we think about that idea of stability. A bond is going to be most stable at the point where the repulsive forces and the attractive forces are in equilibrium with each other, essentially. And so, rather than thinking of a bond as a conventional kind of ball and stick model where the bond itself seems rather rigid and fixed, your atoms are constantly fluctuating. They're getting a little bit closer, a little bit further away. So it's almost like a spring that's bouncing back and forth. And what it's centering around is where we see that valley in this bond energy diagram. So right down here, this would be your most stable spot. On these graphs, you can tell what that distance is. That would be what we would refer to as the bond length, or the average bond length. And the energy, which was typically on the y-axis, that would correspond to the amount of potential energy that's stored in that particular bond. So we call that bond enthalpy. And so, again, the forces that are keeping this optimal length where it is, the attractive forces between the positive nuclei of one atom and the negative electrons of the other, the repulsive forces between the two adjacent nuclei, and the repulsive forces between the electrons of those two atoms that are forming the bond. Now, recall the way that we identify whether or not a covalent bond is going to be polar or nonpolar depends upon how equally the electrons are shared within a bond. And to assess that, we use the electronegativities of the values of the atoms that are forming the bond. And remember that the electronegativity trend for elements increases as we go to the upper right side of the periodic table, with fluorine being the most electronegative element on the periodic table. And so we can always, when we are comparing elements, remember the further to the right we go, the stronger the attraction is going to be, because you've got increased number of protons, effective nuclear charge, and the further up the table you're going, the further up a column you are traveling, the stronger that attractive force is going to be, because you have your valence shell getting closer and closer to the nucleus, so the distance is decreasing. And so when we consider the different types of bonds, again, primarily we're interested in covalent. Covalent bonds are when the electrons are going to be shared fairly equally, sometimes completely equally, in which case, like with oxygen or nitrogen, where literally you have the same electronegativity value, so the difference is zero. But even when there's a slight difference, say between carbon and hydrogen, that difference, depending on what source you're looking at, might be about 0.4. We still consider that to be a covalent or a nonpolar covalent bond, and we consider the electrons to be, for all intents and purposes, perfectly shared equally. A polar covalent bond is going to be one where the tug on those electrons, you think of it like a tug of war, one of the teams in the tug of war, if it's a little bit stronger than the other, is going to be winning the tug of war, but it may not have outright won the competition. And so what happens when we have electronegativity differences between 0.5 and say 1.7, we get what we would refer to as a polar covalent bond. In a polar covalent bond, you have unequal sharing of electrons, and this gives rise to partial charges, partial positive and partial negative. Again, The lowercase Greek letter d, the delta symbol, is what we use to refer to the partiality of the positive or the negative charge. And these are not the same as a full positive charge like we might see on a sodium ion, or a full negative charge that we might see on a chloride ion. Then we talk about ionic bonds. If our electronegativity difference becomes greater than 1.7, then for all intents and purposes, that tug of war has been won, and the more electronegative atom has taken full ownership of the electrons, and therefore we say that the electrons are transferred. So when we refer to this unequal sharing of electrons, that means that the electrons in a bond are going to tend to shift away from the atom that has the lower electronegativity value, the weaker attraction, towards the atom with the higher electronegativity. And that process is formally called induction. And so the greater the difference in electronegativity between two atoms, the greater the inductive effect will be, and the more polar that bond will end up being, until we reach a point where, again, it essentially becomes an ionic bond, where the electron ownership is generally considered to have transferred to the more electronegative atom. So depending on the bonds that we are looking at, if it's a very, very polar bond, sometimes you may see it written as a covalent bond with the partial charges, but other times you may see it written as an ionic bond with a full formal +1 charge or a -1 charge. So for instance, lithium being a metal, carbon being a nonmetal, in very rough general terms, the bond between a metal and a nonmetal we would classify as being ionic. When you look specifically at the electronegativity values, you can see that sometimes it might very much border on the polar covalent spectrum of things in terms of chemical bonding. So in those instances, it's generally accepted to see it written in either of these ways. If we take a look at a molecule, the reason why this idea of induction and recognizing where induction is going to occur is so important is because, again, these are often the areas within the molecule where a chemical reaction will take place. So the 3 steps that we would want to look for in locating partial charges would be: first, identify all polar covalent bonds that are present. We refer to them more simply as dipoles. And so if we look at the molecule here, again, carbon-hydrogen is typically considered to be a nonpolar type bond. Its electronegativity difference is around 0.4, so it's generally considered nonpolar. But a carbon-oxygen bond and an oxygen-hydrogen bond, both of those are prime candidates for induction because oxygen is a very electronegative element. It has a strong attraction for electrons. And so once you've determined or located where a dipole bond is going to be, then you want to determine the direction of each dipole. Now, sometimes we do this with a dipole arrow that points towards the more electronegative atom, or we just simply recognize that the more electronegative atom is going to have the partial negative charge. And so when we put the charges in, the head of the arrow is always going to point towards the atom that's got the partial negative. The tail end of the arrow, which looks a whole lot like a plus sign, is going to be the where the partial positive charge is located. So take a moment now, pause the video, and take a look in your notes or on the screen, and see if you can identify where the partial charges would be by induction in each of these 6 structures. And then restart the video and check your work. All right, so I'll reveal these answers here, and hopefully what you have for each of these matches up pretty well. You can see there can be very few locations where induction is taking place, or it might be very pervasive throughout the entire molecule. It really just depends on the individual example. So again, why is this important to be able to locate sources or locations of induction? Because this is where a lot of times our attacks are going to take place on the molecular structures. And so in this particular structure, hydroxide is an ion that is going to interact and try to attack positive centers, okay? in an organic molecule. So if we can locate where the partial positive locations are, then we know exactly where the anion hydroxide would be attacking. And so if we look by induction, we've got the carbon double bond oxygen. We also have a carbon chlorine bond. Oxygen is very electronegative, all right, so we would expect that to pull the electrons towards itself, and likewise for chlorine. Chlorine is more electronegative than carbon, and so we would expect an induction site there as well.